So we were doing permutations and combinations, and we were done with a number of concepts already. We started with the basic counting principle, and then we talked about arrangements. There were a number of different things I did with arrangements. For example, we talked about how to handle repetitions, identical objects. We also talked about a number of different types of restrictions that can be there. We want some things to be together or we want something separated. In the last session, we did a number of practice questions. We did these questions from the worksheet 37 to 9 and 16. These were the questions that we did from the worksheet in our last session, 37 to 916. Now, we want to move on and discuss what permutations are and what combinations are, right? The topic name was permutations and combinations. So we need to understand these terminologies, that what are permutations and what are combinations. That's what today's class is going to be on. First of all, let's start with permutations. What are permutations? Permutations is basically just another name for arrangements. Permutations is actually arrangements. All right, so this is another word that we use for arrangement. So everything that we've been doing before until now as related to arrangements, they were actually all permutations. Okay, using factorials, multiplication. That was all factorial when where we were. That was all permutation where we were arranging objects. But now here we want to understand a specific notation that is sometimes used that makes things slightly quicker sometimes. That's what we want to understand today, first of all. Now, let's do this with the help of an example. So, let's say we have something like this. We have these numbers from 1 to 9. 1, 2, 3, 4, 5, 6, 7, and 9. We've got these 9 numbers. Now, how many 4-digit numbers can we make using these 9 digits such that no digit is repeated? Now, we've done such examples before, right? So we have 9 digits. We want to make a 4-digit number. So how many places do we have for this? We have to put these 9 numbers in 4 boxes, as in 4 of these 9 numbers in these 4 boxes. Now, how many options do we have for the first box? We want to make a 4-digit number, right? So we could input any one of those 9 numbers here. We've got 9 options for the first box. We could input 1, 2, 3, or any number up to 9. So for the first box, we've got 9 options. Once we have already input one number in the first box, how many options do we have for the second box? We have 8 options. And then you've got 7 and then 6 after that. So if you were to find the total number of 4-digit numbers that are possible using these digits, that would be 9 times 8 times 7 times 6. Of course, the condition is that none of those digits is repeated. You could just evaluate this and see what this turns out to be. That will give us the total possible numbers in this case. Now, if I do this, this is giving me 3024. All right, this is how we used to do it before. Now, we could actually do the same thing using permutation notation. So you actually have a function called permutation, and it has a button on your calculator as well. Remember, in binomial expansion, we used something like this, nCr earlier. We'll talk about this today as well, but right next to nCr, you will see there's another button that's for nPr, and you'll find this on top of the multiplication button. So on your calculators, if you see the multiplication sign, there's a button for that. On top of that, you see nPr written. This actually is the permutation function. So what we're doing here is we have 9 objects and we are arranging those 9 objects, as in some of those 9 objects, in these 4 boxes. In permutation notation, that means 9p4. And that stands for something like this. You want to arrange 4 out of 9 objects. You want to arrange 4 out of 9 objects. And that's what this number is going to give you, 9p4. How are you going to evaluate this on your calculator? You're just going to input 9 on your calculator, then press that button, nPr, and then press the button 4. Press the equal button after that, and that is going to give you 3024. That's exactly what you got here as well. All right. So you could do the same thing that you did manually earlier, 9 times 8 times 7 into 6, 7 times 6. You could do all of that directly using this permutation function, and that will give you the same result directly. That's 3024. Now, how exactly does it work? So this permutation function is actually defined like this. There's a formula for this that the calculator uses. It looks like this. nPr is equal to n factorial divided by n minus r whole factorial. This is the formula for nPr. So for instance, if you wanted to evaluate 9p4 in this case, that would mean 9p4, that equals 9 factorial. That's what you have in the numerator. In the denominator, you would have 9 minus 4 whole factorial. And that simplifies to 9 factorial over 5 factorial. Now, if you think about it, 9 factorial means 9 into 8 into 7 into 6 into 5 into 4 and so on, all the numbers up to 1, right? If I were to write it like this, 9 into 8 into 7 into 6, then after this I'd have 5, 4, 3, 2, and 1. I could write all of them as 5 factorial. In the denominator, I would then have 5 factorial as well. 5 factorial and 5 factorial get cancelled, and we're left with 9 into 8 into 7 into 6. And that's exactly what we were doing here as well. So that same thing that we were doing manually earlier, what we were calculating manually earlier, we could use this permutation notation for that directly, and that would give the same result at the end. This results in 3024. So you just input this on your calculator, 9p4, and that is going to give you the result. All right. So now whenever we've got a set of objects, if they're all different, we could arrange them like this directly. So we could do something like this. If we have n objects, out of them we want to arrange R, it would be nPr. All right. And that would stand for that you want to arrange R out of n objects. That is what this notation is going to mean. So if you have a certain number of objects and you want to arrange some of them, you could use this notation directly, assuming that they're all different, of course. If there were any repetitions or anything, you would have to handle them separately like you used to before. You would divide by the arrangements of the identical objects. That you'll still have to do. But if they were all different, for the numerator, you could just use this permutation notation as well. All right, now let's take an example. Let's say you've got something like this. You've got 11 people and they walk into a room that has 8 chairs in it. How many different possible seating arrangements would there be in that case? Now there are 11 people, 8 chairs. Now, of course, not all of them can sit. Only 8 out of these 11 people can eventually sit on those 8 chairs. But then how many different possible arrangements are there? So you have to do 2 things, right? So you'll be you'll be selecting some people out of 11. So you'll be selecting 8 people and then arranging those 8 people. Now, using the permutation notation, we can actually do it directly. So in fact, before we do that, let's actually think about it logically first. You've got 11 people who walk into a room. It has 11 chairs. It has 8 chairs. If you think about the chairs, so if I were to represent them here like this, let me have the first chair. This is the first chair, C1. Then you have the second chair, C2. Then you have the third chair, C3, and so on until you have the 8th chair. Now, how many options does the first chair have? As in, how many people can possibly sit in that chair? There are 11 possibilities. There could be 11 different people who could sit on this particular chair. So there are 11 options for the first chair. Then once one person has sat here, what are the options for the next person? That's 10. And then when 2 people have already been placed on these 2 chairs, then what's the number of options for the next chair after that? That's 9. And it keeps going on. For the 4th chair, you've got 8. And then for the 5th, you've got 7. For the 6th, you have 6. And then 5. And then finally, for the last chair, you have 4 options. So you could just multiply all of them individually like this. But that's exactly the same thing as saying 11P4. Sorry, 11P8, not 4. 11P8. That you've got 11 people. You want to arrange them 8 seats on 8 seats. So that's 11P8. 11 people, you want to arrange them, you want to seat them on 8 of those seats. All right, and then you can evaluate this and see what this turns out to be. Let me try this. 11P8. 11P8. Okay, so this gives me 6, 6, 5, 2, 8, 0, 0. This is the possible number of seating arrangements in this case. All right. Now, let's think of another example. Very similar to this, but now let's say we've got 8 people who walk into a room that has 11 chairs. So we have reversed that thing. Earlier we had 11 people and 8 chairs. Now we've got 8 people and there are 11 chairs that are available there. How do we think about this thing? 8 people and 11 chairs. Now what we do is so earlier we were thinking about the chairs, right? How many options does the first chair have? How many options does the second chair have? Now in this case, so early in the last example, we actually did 11P8, right? That's what it eventually turned out to be. Now the first thing that might come to your mind in this case would be that now you've got 8 people and you want to arrange them in 11 chairs. One possibility could be 8P11. But that doesn't quite make sense because what this means is you want to arrange 11 out of 8 people. Not people, let's say arrange 11 out of 8 objects. That is not going to work. Even if you were to try this on your calculator, you'll see this will result in an error. It's not going to work. Okay. The number that you have on top here, it cannot be smaller than the number that you have at the bottom. We can't arrange 11 objects out of 8. That does not make sense, right? So this is not going to work. So what do we do instead then? In the last example, we were thinking about chairs. Like how many options you've got for the first chair, how many options you've got for the second chair. But now, since the number of people is less, what we can do now is we can think about people instead. We can start thinking about the people instead. So let's say the first person comes. How many options does this first person have? There are 11 chairs available. It has this first person has 11 options. So this first person can be seated in 11 different ways. So for the first person, we've got 11 ways. Then the second person comes. The second person has 10 ways. Then the third person comes. The third person has 9 ways, and so on until we've got the 8th person. So that's 11 into 10 into 9 into 8 into 7 into 6. That's 6 people. Then 5 and 4. And that's the same thing as saying 11p8 as well, right? What we have done is we've just changed our perspective. In the last example, we thought about chairs. How many options does each chair have? The first chair had 11 options, the second had 10 options, and so on. In the second case here, we thought about people because their number was less. So how many options does the first person have? 11 options. There are 11 chairs available. Then the second has 10, and so on until you've got the 8th person there. All right. So this also turns out to be 11p8. Both of them turn out to be the same. Now, how do we decide what are we going to use in such what we are going to use in such examples? Let me summarize what we have done. So in this case, what you can remember is whatever is the larger number that is coming here, and whatever is the smaller number that's coming here. So if the number of objects that you're trying to arrange is bigger than the number of spaces or places you've got available, then the number of objects comes on top. And if the number of places is more than the number of objects, then the number of places comes on top. All right. If they're equal, then that doesn't matter. That's just going to give you the same thing. Let me actually, before I summarize this, let me go back to some of those earlier examples that we did as well and see how we can use factorials there as well, just to make sure you understand this well. So remember, we started from this example that we had 5 numbers and we had to make a 5-digit number out of them using them. And the condition was that they cannot be repeated. The digits cannot be repeated. So if we were to think about this using permutations, what would this be? We've got 5 objects. We want to arrange them in 5 places. That's 5p5. And if you evaluate this, it's actually going to be the same thing as 5 factorial, and that's 120. So when the number of objects and the number of places where you have to arrange them, that's equal, it's the same thing as using factorial. It results in the same thing. You can try 5p5 on your calculator. That's also going to result in 120. The reason for that is 5p5, if you were to apply the formula, it's going to be 5 factorial over 5 minus 5 whole factorial, which is 5 factorial over 0 factorial. And that is just 5 factorial. So you could also do it using permutation notation like this. It would be 5p5. All right, we did another example in which we had 5 numbers and we had to make 3-digit numbers using them. Now, how does that work? 5 objects, you want to arrange them in 3 places. This could be written as 5p3. You want to arrange 3 out of these 5 objects. Okay, you're not arranging all of them, you're just arranging 3 out of these 5 objects. That's 5p3. And if you were to evaluate this, this would also give you a result of 60. Okay, so we were doing this manually earlier, 5 into 4 into 3. That's the same thing as 5p3. We could also use permutation notation here. Similarly, we did this. We arranged the letters in the word maths. There were 5 letters. All of them had to be arranged. We could also say this is 5p5, and that also results in 5 factorial, which is 120. We talked about repetitions after that. When we have repetitions, we could still use the permutation notation, but remember, the repetitions that you have, they still have to be handled separately. So in this case, if you were to use permutation notation, it would work like this. In the numerator, instead of 10 factorial, you could say you're arranging 10 out of 10 objects. That's just 10p10. Okay, you could do that. In the denominator, you've got 3 factorial, 3 factorial, 2 factorial. That's because we're dividing by the arrangements that we have for the repeated letters. We could do this 3p3 instead of 3 factorial, we could use 3p3. Instead of the next 3 factorial, we could use 3p3 as well. And instead of the next 2 factorial, we could use 2p2 as well. So we could use this in this case, but these repetitions are going to be handled separately in this case as well. Okay, you can't assume that the permutation is going to handle it automatically. Permutation is just an alternative to using factorials here or doing those multiplications manually, but repetitions still have to be handled. But when the number of objects and the number of them that you have to arrange, when that's equal, it's actually much simpler to use factorials directly in that case rather than using the permutation notation. So in this case, you would rather just use this instead of using the permutation notation. That's not really required. Okay, so that's how this permutation notation is related to this. Now let's go back there and summarize all of this that we have discussed here. So how are you going to use this permutation notation? So when you're arranging objects, let me write this down here. While arranging objects, if you want to use permutation notation, this is the rule that you can follow to decide whether you should be using permutations or factorials. So if the number of objects that you have is equal to the number of places or spaces in which you have to arrange them, if both of them are equal, if there are 5 objects, you want to arrange them in five places. In permutation notation, that would be n objects and you have to arrange them in n places. That's the same thing as n factorial. So in such cases, you would rather just use factorial directly. Okay, there's no need of using the permutation notation in this case. All right, if you wanted, you could still use that, but it's not required as such. But in cases where the number of objects that you're trying to arrange is not equal to the number of places in which you're trying to arrange them, in that case, what you do is you use nPr. Then you use this notation. In this case, you use nPr. But how do you decide what is n and what is r? N is going to be whichever of these numbers is bigger. So n is whichever out of the number of objects and the number of places is bigger. That is going to be your n. So that's the number that's going to come on top here. And r is going to be whichever of those two numbers is smaller. So that's exactly what we did in this last example, in this earlier example that we did. We had 11 people that walked into a room that had 8 chairs. We said it should be 11p8 because the number of people was bigger than the number of places. We took 11 at the top here and 8 at the bottom here. And in the other example, the number of people that we had was less and the number of places that we had was bigger. In that case, we took number of places on top here and the number of people at the bottom here. All right, so whatever is the larger number, you put that on top. Whatever is the smaller number, that comes here. All right, so this is the summary that you can use for permutations. So this is what you need to know about permutations. Now, I hope that makes sense. If you have any quick questions, let me know. Otherwise, I'm going to move on to combinations now. All right, let's move on to combinations then. So permutations was basically just arrangements, but now we've got this new notation that you should be familiar with. Now, let's move on to combinations. Now, what are combinations? Combinations are basically about selecting objects out of a certain number. So for example, if you have a group of 30 people, you want to select a certain number of people out of that. So if you're selecting a sports team, let's say there can be 11 members of that team, and you have a total number of 50 people out of which you can select that team. Now, it doesn't matter who you select first in those 11, amongst those 11, and who you select second, who you select third. The order of selection does not really matter. All that matters is who are the 11 people who are eventually selected, right? It's only the people or the objects that are selected that matters. The order is not important in this case. All right. This is what combinations are, that we just want to select objects. Okay. In this case, the order of objects is not going to be important. Now, let's take an example, try to understand using an example. We've got something like this. We want to figure out how many different teams of 2 people can be made from 3 people. Let's say they're labeled A, B, and C. How many different teams of 2 people can be made from this? Now, if you were to use permutation here, how many, what's the total number that you've got? You've got 3. And how many do you have to select? 2. 3p2, that would have given you 6. But write down the total number of teams that are possible. It's a small number, so you can actually just write all of them down. The possible teams could be AB, you could have AC, or you could have BC. There are actually just 3 teams possible. There are no other teams possible. What permutation does is it actually calculates their different arrangements as well. So it considers these two to be different teams, AB and BA, and similarly AC and CA, and BC and CB. It considers these two, and these two as separate teams. So we can't use permutations here. That is not going to work. So what do we do instead? We have that combination button on our calculator for this. Instead of using permutation, we use combinations here. We say this is 3C2. Remember, we used to do this for binomial expansion. This is actually where that function comes from. It's actually a combination function where you are choosing 2 out of 3 objects. What's the number of possible ways of choosing 2 out of 3 objects? If you were to try this on a calculator, 3C2, this gives you 3, and that is what you were actually looking for. So what does this notation mean? nCr, this means you want to select, you want to choose R out of objects. Earlier, we were arranging objects. In permutations, we were saying arrange R out of n objects. Now this is select R out of n objects. Now the arrangement does not matter here. So this turns out to be 3 here instead of 6. Okay, so when you have to select objects, you use combinations instead. Now, there are some keywords that you should be familiar with that would give you a hint that you are actually using, that you actually need to use combinations here and not permutations. For example, one keyword is what you've used here, that's called selection, right? So whenever you have to select something, that gives you a hint. You're looking for a combination. Whenever you have to choose something, or you want to make a group of some people or a team of some people, all of these keywords, they basically represent that the order is not important. It's just the group that's finally selected that matters. When you have permutations, on the other hand, you would mostly see the keyword arrange there. So permutations are mostly about arranging objects, right? In combinations, these are some of the keywords that you will see being used in the problems. All right, now let's take another example. Let's take another example and try to understand how this combination formula works. Very similar to the last example, how many different teams of 3 people can be made from 4 people, A, B, C, D, all of these are different people. We could just say this is 4C3, right? We want to choose 3 out of 4 people. And the number of possibilities that you end up getting for this is going to be 4. All right. Just evaluate this on a calculator. You get 4 for that. Now, can we list down all of those cases? One possibility could be A, B, C. You could have A, B, D, and then you can have A, C, D, and B, C, D. These are the 4 possible teams that you could get from this. Now, if you were to use permutations instead, what does that give you? That gives you 4P3, and that number is 24. Yeah, that's 24. 4P3 is 24. Where would that come from? Basically, permutations would count each of these teams 6 times, 3 factorial times, because in how many ways can you arrange this team ABC? You can arrange this in 3 factorial ways, right? You can arrange this in 3 factorial ways as well, this in 3 factorial ways as well, and also this in 3 factorial ways. So permutations is counting them as 24. But since we are not really interested in the order of these letters, to us, only these 4 unique cases are important. But from this, we actually get a useful relationship between permutations and combinations, and that looks like this. Permutation is giving us 24. If you were to go from permutation to combination, what would you have to do in this case? You've got 24, but this 24 is counting each one of these outcomes or each one of these different teams as it's counting each one of these teams 3 factorial times. It's counting each one of them 6 times. So in order to get unique number of teams, you would divide by 3 factorial. And that would give you the actual result, which is 4 here. Now, why is that relevant? The nCr formula looks like this. nCr formula is n factorial over n minus r whole factorial into r factorial. Now, this part of it is actually the permutation formula. So this thing can actually be written as nCr equals nPr over r factorial. And that is exactly what's happening here. In the numerator, this is 4p3, and you're dividing that by 3 factorial, and that is giving you the number of combinations, which is 4c3. So this relationship between permutations and combinations, this is important because this can be rewritten as or rearranged as nPr equals nCr into r factorial. So permutations and combinations are related to each other using this formula, using this equation. So what does nPr mean? This means you want to arrange R out of n objects. What do you have on the right side? On the right side, nCr means select R out of n objects. Select R out of n objects. And R factorial means arrange those R objects. So when we say nPr, that means we want to arrange R out of n objects. That's equivalent to saying we are choosing R out of n objects first. That's one thing that we're doing. And so this multiplication sign stands for and. Then we are arranging those R objects. So permutation is actually doing two things at the same time. It's selecting R out of n objects, and then it is arranging those R objects. It's doing two things. So sometimes what would happen would be that you will have to select something, you'll have to arrange some objects, but there will be some kind of restriction on their selection, first of all. There might be a certain number that you might want to select from a certain category and another number from another category, and then you want to arrange those things. In that case, you cannot use the nPr formula directly. You'll have to split it up. You'll have to first select the required objects using the given conditions and then arrange them after that. You'll have to split this process into two parts. So even though you will be asked to arrange something, you would say, let's choose them first. Once you've selected them, then you would arrange them after. Okay, so we'll see that in a couple of examples in a moment. Let's try to understand what is meant by this, or by all of this, what we've done about combinations, using a few examples now. Let's say we've got a delegation of 3 boys and 4 girls that is to be selected from a class consisting of 10 boys and 15 girls. Now, how many possible different delegations can be selected given these conditions? How many people do we have in total? We've got 10 boys and 15 girls. That's 25 people in total. Out of those 25, we need to select 7 people. Now, if we were to just do 25C7, that would not work, because in these 7 people, we are not applying any restriction that how many boys need to be there and how many girls need to be there. It's just selecting 7 people randomly. So you might end up with all girls or all boys or more girls or more boys than girls, which does not satisfy this condition. So you can't do it like this. It doesn't work like this. What you do instead in such cases is you say, there are 10 boys. Out of those 10 boys, you want to select 3 boys. That means you have 10C3 for that. And basic counting principle, remember? You multiply with what? You need to select 4 out of 15 girls. So that's 15C4. You choose the boys separately, making sure that their condition is met, and you choose girls separately, making sure that their condition is also met. So that's 10C3 into 15C4, and that's going to give you the result. This gives me 163,000. That's the total number of possible delegations you could have out from these 25 people, given that these conditions are met. All right, let's take another example. Let's say we got something like this. There's a group of 12 people, 8 boys and 4 girls. We need to arrange 3 boys and 2 girls from this group in a straight line. in how many ways can this be done? Now, this is where this thing is going to be important, where we said we sometimes have to break it down, that we select objects once and then we arrange objects. Because in this case, you see, there is a condition that you have on selecting, and then you have to arrange those people. So let's take 10 seconds to just read this statement first of all, and then we'll try this. Okay, so there's a group of 12 people, 8 boys and 4 girls. We need to arrange 3 boys and 2 girls from this group in a straight line. It's arrangement. All right, so we need to arrange these people. But there's a condition that we need 3 boys and 2 girls. Now, if we were to arrange them directly, 12p3, no, not 12p3, 8p3, the 8 boys, out of those 8 boys, we need to select 3. We need to arrange 3. And then if we were to say 4c2, because out of 4 girls, we need to arrange 4p2, I'm sorry, 4p2, because out of 4 girls, we need to arrange 2. That would not work, because what this means is we are arranging the 3 boys separately, and we are arranging the 2 girls separately. Okay? But they all have to be arranged together. You could also have something like this, that you have 2 boys and then a girl, then a boy, and then a girl. That's also possible. But that possible arrangement is not being accounted for in this case. So you can't do arrangements directly here. You can't use permutations directly. What you'll have to do in this case would be that you first choose those people considering the required condition. So you want 3 boys out of 8. That would be 8c3. And you also want 2 girls out of 4 girls. That would be 4c2. Now, this ensures that you have selected the right number of people, right? The right number of boys and the right number of girls. Once that is done, now we want to arrange those people. There are 5 of them. In how many ways can we arrange 5 people? We could just use 5 factorial for that. And that would ensure that all of the arrangements are accounted for. And that's going to give you the result. All right. So in the first part here, what you're doing is you are selecting 3 boys and 2 girls. Once you've selected all of those 5 people, now you are arranging those 5 people. All right. This is how it works. So you can sometimes, do it in steps. First choose something and then arrange them. Let's take another example. Let's say there are 5 people, A, B, C, D, E. You need to select 3 of them for a competition. What is the probability that a randomly chosen team would have B in it? There are 5 people, A, B, C, D, E. You need to select 3 of them for a competition. What is the probability that a randomly chosen team would have B in it? Now you've got probability along with permutations and combinations, right? So you also have to take care of this probability now. Now, how is this going to work? Now, remember what the probability formula was? Probability was defined as number of favorable outcomes divided by the total number of possible outcomes. That's how the probability formula looked. When you have permutations and combinations, you can actually use the same formula. And you could say, if you have combinations or permutations, the probability formula would become something like this. So if you had permutations, if you had to find probability of a certain number of permutations, you would say that equals number of favorable permutations divided by the total number of possible permutations, total possible permutations. Okay. Similarly, if you had to find probability for a certain combination, again, you would find the number of favorable combinations and divide that by the total possible combinations, and that will give you the result. All right, let's use this here. There are 5 people, A, B, C, D, E. You need to select 3 of them for a competition. Now, what if there was no restriction? If there was no restriction, the total possible combinations, what would they be? Total possible combinations. Let's write this here. First of all, total possible combinations, that's just 5C3 if there was no restriction. So that's your denominator. The total possible combinations without any conditions. All right, this turns out to be 10. Now, what's the condition? The condition is that a randomly chosen team has B in it. The condition is that the team should have the person B in it. That person should be there in the team. Now, what's the possible number of combinations if this condition is met? You've got A, B, C, D, E. You've got 5 people. You want to select 3 out of them. And now the condition is B should be in that team. What would we do for this? We can say there are 3 places, right? But we know that B has to be there. So B is already selected. We had A, B, C, D. These were the 5 people. Out of them, B is already selected. So B is gone from there. We have 4 people left now. We only have option for these 4 people now. 2 out of these remaining 4 people have to be selected. So what's the possible combinations in which you have B, the possible number of teams that have B in them? That is going to be 4C2. These are the teams that have B in them. Teams containing B, that is 4C2. Containing is actually used for objects, I think. Teams that have B, that's 4C2. 4C2 is going to be 6. So what's the probability? That's number of favorable outcomes. That's 6 divided by the total number of outcomes, 10. And that gives you 0.6. That's the probability that a randomly chosen team would have B in it. All right, that's 0.6. Make sense? Now, there is one more example that I wanted to discuss. So this is about probability. Whenever you have probabilities and you think there is going to be some use of permutations and combinations, what you do is you find the number of favorable combinations and divide that by the total possible combinations. And that's exactly what we've done here, right? Similarly, you could do the same thing for permutations as well. There's one example that I wanted to do, but we're running out of time. I want to start another class as well. Think about this for tomorrow. We will discuss this example in our tomorrow's class. So basically what happens is when you have repetitions and you want to select a certain number out of them, this is something that cannot be handled directly. Unlike permutations, in permutations, we had a specific formula for this in which we just divided by the arrangements of the repeated objects. We can't do the same in combinations. In combinations, we end up having to make different cases and then finding the required selections from that. But we'll discuss this in the next class. I'm running out of time. We'll So we want to select 2 letters out of these 4. Think about this in how many ways we can do this. We'll discuss this tomorrow. That's it for today. I'll see you again tomorrow.